Hi, let's take a look at the topic of continuity and how that will be seen in Calc 1. And what we first need to refresh our memory on is how to find the domain of a function. And in particular, in this first one right here, you'll see we have g of x equals square root of x squared minus 9 all over sine of x over a given interval. So the first thing that I'm going to actually do is remind myself that I have this closed interval. And so I'm going to make a number line. But instead of it being open on either end, going negative infinity to infinity, I'm going to close it because it's going to start at 0 and end at 2 pi. And typically when trig is involved, you might see some form of 0 to pi, 0 to 2 pi, something like that. 2 pi is the same place on the unit circle as 0, so that's typically why we only include one of those. But they might both be included, so you'll just have to go with whatever closed interval you are given. So the first thing that we're going to do is take a look at this numerator here. So square root of x squared minus 9. And what you might remember is that when you have an even root, so second root, fourth root, sixth root, etc., your radicand, or what's underneath this square root right here, needs to be actually greater than or equal to 0, because I could take the square root of 0. So not only does it need to be positive, but it could also be 0. If it's in the denominator, it cannot be 0. So x squared minus 9 is greater than or equal to 0. If I think about where is it equal to 0, hopefully we can see that x squared minus 9 would equal 0 at plus or minus 3. Well, that's not the question. The question is, where is it greater than or equal to 0? So if we think about that kind of on its own little number line here, negative 3 and positive 3, and if I think about numbers in this section right here, so maybe smaller than negative 3, like negative 4, negative 5, etc., when you square it, that's something like 16 or 25, and when you subtract 9, you still are in fact positive. Same thing is true with values over here. But if you pick something in between there like 0 and you try to put that back in for x, you get a false statement. Negative 9 is not greater than or equal to 0. And in other words, if you look at this graphically, you have a quadratic, which is just a parabola that opens up, and it's shifted down 9. So it looks something like so, where this is negative 3 and this is positive 3. So we can see that we are greater than 0 on those ends. Okay, so I know that x has to be either less than negative 3. Well, negative 3 is way over here. So that's not even a part of my closed interval anyway. But it has to be greater than 3. So I just mark 3 here. And it could be or equal to. Remember, because it was in our numerator. So I'll say greater than or equal to 3. So I'll put a closed point or a bracket, whichever you prefer. And I'm heading this way so far. So none of these are even an option anymore. And then now if I look at my denominator, sine of x, well, we can't divide by 0. So let's take a look at where is the sine of x 0. And again, on a unit circle, if we think about that, that would be, for example, at 0 and at pi. So you could write the statement one of two ways. Sine of x equaling 0 is really the equation that I'm trying to solve. But you're saying that sine of x cannot be 0. So if you like the cannot equals, that's appropriate as well. So x cannot be 0, pi, 2 pi, etc., right? Because you could go around the unit circle again and again and again. And so pi is after 3, because 0 is obviously already not included. So I would put pi on here, and that needs to be an open circle. And 2 pi, I already have a parenthesis on. Okay, so if I write this answer out now in interval notation, I would say my domain would be from 3 to pi, union with pi to 2 pi. And again, we have to have parentheses around the pi because we cannot include pi. And now let's check this out graphically and see what this looks like. Okay, so let's look at this graphically here. I have typed in the function square root of x squared minus 9 all over sine of x. And it is an interesting looking function here. So we're going to zoom in and just take a look at the piece that we want to look at. And as I do that, I want you to pay attention to the x equals 3. So when we get to that point, I want you to see what that looks like. Okay, here might be a better window. And what we'll notice is that certainly our function does not exist between -3 and 3 because that was one of the initial domain restrictions that we talked about. But what appears to be a vertical line coming off the -3 and the 3, the x equals 3, is actually not. So what you can see, and if you click in Desmos, you can see various points along the way. So this point, for example, right here is 3.12. So it is increasing in x value. Again, this is a function, so we would want it to pass the vertical line test anyway. So the only value at my function at x equals 3 is an output or y value of 0. And so what we can see then, if we're just looking 0 to 2 pi, we're just looking 0 to just after 6, so just right around here. It starts at 3, so that's correct. And then we do have a point of discontinuity here at pi, which is approximately 3.14. And again, if you look at some of these values, you can certainly see that. And then again, it's going to have another vertical asymptote here at 2 pi. So our domain does match what the graph looks like. It's kind of a neat graph. So again, algebraically, that graph did match our domain that we stated. All right, so moving on to question 2. Let's take a look at something without trig. So this does not have a closed interval to it, so I need to look -infinity to infinity. So that's the first thing I'll map out here is I am looking -infinity to infinity until otherwise stated. And now when we look in our numerator, it is a cube root, and we do have to pay attention to that. So now, even though my radicand is still x squared minus 9, so we think, oh, positive and -3, yeah, but we can take the cube root of a negative number. Cube root of -8, for example, is -2. So there is nothing wrong with this. There's no domain restrictions with this cube root of x squared minus 9. It could be negative. The cube root of 0 is 0, and it's okay to have 0 in my numerator. So this part right here gives me no domain restrictions. Okay, so now I have to look at the denominator. And we know that our denominator cannot be 0. And so again, if you prefer to solve this equation where it equals 0 and then put the cannot equals in, that's fine too. I'm going to factor this. And so because of my zero product property, I know that x cannot be 3 and x cannot be -2. And so on my number line, I would add those restrictions in order. So -2 comes first, so that would have a point of discontinuity there, and 3, and that would have another jump or point of discontinuity. And you'll talk in calculus about whether these are vertical asymptotes or holes. You'll also see it graphically if you choose to graph to check. I have no other restriction, so this is what it should look like in terms of the domain for this function. And so I'll write that out in interval notation, -infinity to -2, jump on the other side of -2 to 3, and then 3 to infinity, and that should be my domain. And if we check it graphically, here's my cube root of x squared minus 9 all over x squared minus x minus 6 as a function, and that's exactly what I see. X cannot be -2, and x cannot be 3. I'm going to see those vertical asymptotes there. You can try to calculate as well, especially if you're on a TI grapher. You can calculate a value. You can add sliders in here in Desmos to show you that it does not have a value as well. All right, so let's look at number 3 here. So this one is trig, and this also has another closed interval, so that's what I will start with. I'm only going to be concerned from 0 to 2 pi. Okay, so let's look at our numerator first. Now, tangent of x. So what we need to look for are where are the discontinuities for tangent of x as a function. Well, since tangent of x is really sine x over cosine of x, all those discontinuities or vertical asymptotes will take place when cosine of x is 0, and that will take place at pi over 2, negative pi over 2 if I was looking to the left, and then every pi after that. In other words, if you remember the graph of tangent of x, it looks something like so, and it is cyclic or periodic, so you'll see it over and over again repeat itself, and the period was pi, and so that's why half of a pi, or pi over 2, is on either side for the vertical asymptotes. So I know tangent of x itself has discontinuities. I cannot put pi over 2 in for x. That'll give me an error or a domain restriction in my numerator. So I already have pi over 2 to add to my number line. That's one jump, as well as 3 pi over 2 is another jump. Now let's also look back at my denominator here. Well, 2x minus 5 cannot be 0. So, okay, x cannot be 5/2 when I solve that, and then I identify, is that in my closed interval and approximately where? Well, 5/2 is 2.5, so I might need to think of these as decimals. So if you think of pi over 2, again, pi is about 3.14, so this is more than 1.5, so it's bigger than that. But 3 pi over 2 is about 4.5, so 2.5 somewhere in between here. And so here would be my domain. Just have to exclude that 5/2 as well. And if we write that out in interval notation, we exist from 0 to pi over 2, and then from pi over 2 to 5/2, and then from 5/2 to 3 pi over 2, and then 3 pi over 2 to 2 pi. And so you could definitely check this one graphically to see that that's the case. You should have a vertical asymptote at about 1.5 for pi over 2. And you should have a point of discontinuity or another jump, vertical asymptote at 5/2, and then again at 3 pi over 2. And so if we graph it, that is exactly what we see. So again, we're starting to look at 0. So after 1.5 here, you'll see this is like pi over 2. Okay, I have a vertical asymptote or a jump, point of discontinuity. And then I'm doing great until I get to about 2.5. And then again, I'm doing great until I get to that 3 pi over 2 value, and then I'm fine until after 2 pi. So our domain matches what we see. Okay, so hopefully you're kind of getting the idea of this. So one more here, x squared minus 16. There is absolutely no restriction here from this because number one, it's not under any square root or fourth root or sixth root. It's just in my numerator, so that value could be negative, could be 0, could be positive. That's not impacting at all. I need to worry about cotangent of x. Now there's two things that have to happen here. So cotangent of x itself has its own discontinuities. It as a graph, cotangent looks something like so, where it also has a period of pi. So all of those vertical asymptotes are pi apart. So the first one, so to speak, if we're looking in our closed interval from 0 to 2 pi, I'll draw that number line for us. The first one does occur at 0, so I already cannot be 0, so I'm going to change that to a parenthesis. This is x equals 0 as a vertical asymptote. This next one here is at x equals pi because it's pi apart. So I can't equal pi, so I'll make that a jump. And then same thing with 2 pi, but it's already not included, so that's okay. So you would think you're done, but remember your denominator also cannot be 0. Cotangent being in the denominator means cotangent of x cannot be 0, and I need to solve that trig equation. So you can do this one of two ways. You can remember what cotangent of x is, so that is cosine of x over sine of x. And our fraction becomes 0 when the numerator is 0. So now I have to look at wherever cosine is equal to 0, I'm going to run into these domain restrictions. So, okay, well that is at pi over 2, 3 pi over 2, etc. Again, I only listed positive ones because knowing my closed domain here starting from 0 to 2 pi is really all I'm concerned with. The other way is you have a graph. This is a graph of cotangent of x, if you remember it graphically. So everything is periodic. This one doesn't look necessarily quite symmetric, but it is. You cross through that x-axis halfway through that interval, and if the interval was pi, let's just look at this first one here, then we cross that x-axis at pi over 2. So that's another way that you can kind of look at that. All right, so pi over 2 is a restriction, and 3 pi over 2 is a restriction, but x can be anything else. And so I should see that if I graph it. Again, if you're using your graphing calculator, make sure you're in radian mode, and I'll just write out the domain in a positive way, that my function would exist from 0 to pi over 2, union that with pi over 2 to pi, union that with pi to 3 pi over 2, and union that from 3 pi over 2 to 2 pi. And there's my finished domain. Okay, one more. Let's graph a piecewise function. What you're going to do in calculus is you're going to actually make a piecewise function continuous. So for now, let's just work on how do we graph this as a function. The first curve, which I'm going to draw in this purple color here, x squared minus 9 would be a parabola, and it's only good for these x values, so that's the piecewise. And there's actually a lot of practical applications for piecewise defined functions because certain trends seem to hold for certain periods of time, and then given a different time interval, a different pattern holds true. And then the same thing is true for your third function. So we kind of have three pieces to this. So I'm going to graph the first piece in this purple color, and it's a parabola that opens up, and it's shifted down 9. So I'm only going to label here what I need. So it's shifted down 9, parabola that opens up. And again, we're graphing this on a Cartesian coordinate plane here, x, y, so I did label those axes. And so here's my curve, but this is only good for values for x less than -3. So what I'm going to do is figure out where is my curve at x equals -3. Well, that is the point -3, 0, so right here. And it's only good for values less than -3. So what I'm actually going to do is make that a open point at -3, 0. And I'm going to erase all of the x values that are greater than -3. So I'm going to erase the whole rest of this parabola. Now, do you have to draw the whole thing and then erase it? No. I'm just sort of showing you that you know exactly what that looks like. The other reason why I graphed that first is because you might think that that's a vertical line coming out or up from -3, and it certainly is not. It's just maybe the way I drew it, it looks like a vertical line. But again, we're a function, so it certainly is not. That's the first piece of my piecewise. Now the next piece of this piecewise is only good for values for x between -3 and 2, and it's inclusive in both. So I might want to see where each piece starts and ends. So we did say that this is going to actually end at a whole -3, 0 for the first one. I just wrote down what we verbally said. Let's figure out where this second piece starts and ends. Both of these will be points. And if I put -3 in for x into this middle function here, 2 times -3 gives me -6. So it starts at -3 for x, comma -6 for y, and it's going to end at x equals 2. So if x is 2, 2 times 2 is 4, so I have the point 2, 4. And again, I should recognize 2x, if you want to rewrite it like this, as a line with a y-intercept of 0 and a slope of 2. So I could draw it that way as well. So I could draw it something like so, right, where I have a line, y-intercept of 0, slope of 2, so this whole line is y equals 2x. All right, well, it's not going to go on forever in either direction. Remember, we said it starts at -3, -6, and that's a point. So I'm just going to make this x equals -3 and y equals -6. So that's just -6 right there. And then 2, 4 is also where it ends. So maybe that's right here. I'm going to label the point, and I'm going to erase all the rest. And then my third piece of this is going to start at a whole 2 comma something. Well, let's figure out where something is. See, it starts x is greater than 2. So if I put 2 in for x, 6 minus 2 is 4. So I would make this a whole at 2, 4, but see, it's already closed in, and it has a slope of -1, so it looks something like so. So I do have arrows on the end. See the arrow on the left end and the arrow on the right end, but in between you are disjointed. And so my final overall graph kind of looks like this, parabola that opens up over here to the left. Make it a little thicker. Open hole there at -3, 0. Closed point at -3, -6. And this does not violate the vertical line test because, see, at the x value of -3, you're defined at -6. And then I have a line connecting, and here's a point, 2, 4, and then I have a negative sloping line for the rest. So the only place where I have a jump or a point of discontinuity is at that x value of -3. I am actually continuous right there at that point where x equals 2. I hope that helps give you a refresher on some of the piecewise defined functions and how to graph them. Thanks for watching.